I'm going to tell you about explicit results from the gauge mean field calculation and as well as numerics like quantum Monte Carlo. Okay, so we are talking about quantum spin model and with some very complicated interaction terms. This is a case where we get we have only three types of interactions. One is the Ising interaction, and this is a U1 symmetric exchange coupling, and this is what I call Q-term or S plus interactions. And in that case, as I already told you, U1 quantum spin legged phase or Coulomb phase is stable when this guy is negative, or actually this has an opposite sign with delta. So when delta is positive and this guy is negative, I just like to remind you that we have okay, so in this notation, actually, this delta is delta half is minus j plus minus divided by j. So it's opposite sign. It has opposite sign. So in that case, I already explained that there is a line degeneracy in the spin-on excitations in the lowest branch. And so it's quite hard to get Bose condensation. So then U1 quantum spin leakage is stable up to a very large value of this number. And actually, it actually goes beyond the Heisenberg point, so that we cannot rely on this theory. But in any case, it's clear that on this side, actually, U1 spin leakage is quite quite stable. And on the other hand, if we go to the other direction, so then we still have U1 quantum spin leakage ground state here, but at the end we have a weakly first order Higgs transition to Bose condensed phase with a charge 1 Higgs aspect. And then we have a ferromagnetic order of the spins in this notation, in the local coordinate. And actually, all these spins, Hamiltonians, are written in local coordinate frames, which are actually invariant under the C2 rotational symmetries operations. Then that phase, planar ferromagnetic phase, actually is nothing but anti-ferromagnet with well, it's quite hard to draw spin patterns here, but I think this should be like this. This is actually the symmetry is reduced to a tetragonal from cubic. And actually, the symmetry is I41 slash and D like this. And this is the magnetic space group. But on the other hand, if we go to this direction, so then we have another phase transition at the finite coupling constant. And this gives another phase which has like this. It's hard to, capture the stereographic image, but in case they are different order. And in the particular case of the non-Kramers doublet, where we do not have this last term, so then this model is actually good enough, at least as far as nearest neighbor models are concerned. So then this could describe, praseodymium pyraclodes and also the terbium type pyraclodes, right? So in that case, I already mentioned that S plus or S minus represent quadrupole degrees of freedom, actually electric quadrupole. So it means that if we have a long-range order in a planar spin components, so then we have a electric quadrupole long-range order. So that could be detected by, for instance, polarized neutron scattering experiments. But at the moment, no experiments have been done to detect these kind of orders. Probably one of the reasons is that polarized neutron scatterings are quite, expensive, and also try to get a high intensity is quite hard. Okay.
I mean by when you mention electric quadrupole, it means that there is no spin dipole matrix element between the two members of the doublet.
Mm-hmm. Yes.
But you may have higher order. What would be the first
so this is
element you have?
Yeah, so this is the next order.
So it would be S.
Okay, I can tell you more
it can
details.
also spin quadrupole.
Okay, I can tell you more details. The reason why I would just say that it is just a quadrupole degrees of freedom, and of course it may be accompanied by higher multiple, higher multiples. But in this case, actually, if we take ground state doublet, which can be labeled by just plus minus. So then this could be, for instance, some linear combination of the states like mj equal to 4 and 1 and then minus 2. Right? And this should have a plus minus sign, plus minus, and minus plus. Okay? And there should be some parameter here. And because of the symmetry, we need some minus sign here for the lower case. And yeah. So then what we observe is that we can construct matrix element between the different doublets. There are different states in the doublet. And if you take actually the diagonal component, so then actually we can find a finite matrix element between the diagonal, the same states for JZ. And magnetic moment has several contributions. That is G mu B times 2 mu B times G parallel plus G perpendicular and X and Y. Of course, they have some direction. Like this. So if we talk about some elements in a magnetic dipole, so then we can just compute the average of the, expectation value of the Jz or Jx or Jy. Okay. So then it is kind of straightforward calculation, and results is that for Jz, this becomes simply 2G mu B times some coefficient, which depends on these parameters, and yeah, something. And this is not 0. But for Jx or Jy, this is operator which changed the quantum number by just 1, right? So that actually, you can do that, but there's no matrix element. So this is always 0, and independent of the states here. And then the next thing to do is just compute the product, actually the symmetric product, like this. And this is not 0. That's why I'm saying that this is a quadruple. And of course, it contains a higher order multiples. Yeah.
So this would be that the spin quadrupole. Why do you use electric quadrupole? Why not simply spin quadrupolar operator has a finite matrix element?
Sorry, can you speak up?
This is a spin quadrupolar operator.
Spin. This is actually pseudo spin. This is just pseudo spin. This is the operator actually operating onto the local doublet. And these doublets are not
Jz satisfies the SU2 algebra.
SU2 algebra.
It's a spin operator. Right, so the J square, or J alpha beta, J alpha times J beta, it is a rank 2 tensor or whatever, so it's a spin quadrupole. So I was confused by electric quadrupole, not spin quadrupole.
It's not magnetic quadrupoles. It's not a magnetic quadrupole. Actually, it requires multiple expansions of the multiple expansion of the probably potentials or okay. So if we have a magnetic quadrupoles, then we should have some non-uniform distribution of the magnetic dipoles, which might not be ordered or might be ordered. And this is a kind of local quantity, and it strongly depends on the orbitals. Okay, and actually this is nothing but kind of orbital order with some relativistic effects. Okay, none of spin or orbitals are not going to quantum number in the atomic limit or in a ionic limit. And this is kind of a mixture. And people usually say when we have this kind of element, this is an electric quadrupole. But not actually. This is distinct from the ionic quadrupole. Now maybe I can tell you more. I later. If I see a node, then it's clear. Okay. So then these are the electric quadrupole states, and they have a different order. So if they perform inelastic neutron scattering, polarized spin polarized neutron scatterings, then actually they can distinguish between two. Or there could not be any long-range order, depending on the sample or systems.
What is P stand for PF?
It's that abbreviation of the planar ferromagnetic or planar antiferromagnetic. I wanted to say that it's not a long-range order of the Z component of the pseudospins, but transverse component.
So this transition from a spin liquid to this PFXY is a first order transition?
Yeah, in a strict sense, it's a first order, but if we just perform honestly the mean field calculations,
You will not find the first.
right? So because it's just a weakly first order, so it's usually in the mean field level, or it's
So
second order.
You have to add fluctuations. The
Right.
flow takes you.
Right, exactly. And but this transition is already a first order in the mean field level. Okay. And actually, I will try to introduce some experimental results from Japanese group and on terbium titanate that some sample of this material is located around here. So it's in a ferroquadruple state. But it's not just, it's just analysis of the experimental data and try to capture the experimental features by fitting, by optimizing these coupling constants. So we got coupling constants which are located around here. So it should be a ferroquadruple order state. But that experiments have not been performed yet. Okay.
As people are numerics on this spin liquid to expect the order of the transition is. See, if I do scalar QED, for instance, only in 4 minus epsilon you will get the first order. First order transition.
Yes.
If you really do simulations.
Yeah, I will show it. Okay. So now try to check the validity of these analytical arguments. Some of them may be valid, but some of them other might not be valid. So, but to facilitate the calculations, let's take the simplest model, which doesn't have a negative sign. So this model is already not that trivial. And this is just the XXD model with antiferromagnetic coupling J, and we take J perpendicular as ferromagnetic. So we perform quantum mechanical simulations in imaginary, continuous imaginary time using the path integral approach and based on a loop algorithm. So which would be explained by Sandvik in this school. But we did not take a stochastic expansion approach, series expansion approach, but we took a continuous time because most of the time, actually we can gain some advantage by taking a continuous time. The reason is very simple. So we are interested in the case where the coupling constants here is small, right? So most of the time, if we perform the SSE, then most of the time we'll be just having this term. Most of the weight comes from this term. But actually, this can be treated as a diagonal term, so without any vertex in the continuous time algorithm. And so we can skip this term, but just say that the probability for finding a kink or the spin exchange. So that's a kind of rare event when this coupling constant is very small. So in that way, we can virtually integrate out degrees of freedom, some degrees of freedom associated with the diagonal terms. Okay. So then we got some results, and this is a phase diagram, J perpendicular versus temperature T, and in a logarithmic scale in this vertical axis. And this, note that this is on the negative side of the coupling constant, so that there's no negative sign problem, or we have a phase transition as predicted in Yates theory. Okay, so here is some results on specific heat. Actually, we derived this specific heat by taking the numerical derivative of the total energy, total energy, and then we integrated out the specific heat by the T temperature to derive the entropy. That's a kind of change in the entropy during the temperature on heating from quite low temperature to high temperature. So then we found okay, so we start from this case where the J perpendicular is around minus 0.2.
JPEG, when you write your Hamiltonian, this is in local basis or global basis?
Excuse me?
Your axis, they're on local basis or global basis?
Actually, it doesn't matter if we talk about the XXZ model, because there's a U1 symmetry. But you can think that this is in a local basis. But I mean, okay. So then, local basis. Okay, so maybe this is the reason why you're confused. So we got the planar ferromagnetic order, long-range order here on heat on cooling in this direction. And remember that previously in the gauge theory predicts the critical value. I mean, the transition point for J perpendicular is given by around minus 0.2. But actually, it's already deep in the ordered phase. Okay, and there was already a previous calculation by Banerjee et al., and which is given by these 2 points. And they already claimed that there is a phase transition to this ordered phase. Okay, and this is kind of a trivial cases where we have a long-range order, and the long-range order can be also detected by seeing the growth of the specific heat peak here on increasing L. Okay. And the more interesting happens when we take this parameter with a much smaller number for J perpendicular. So then here is the energy, total energy, and this rapidly decays on cooling below T equal to 10 or 1. So then there's a crossover as we see in a Schottky peak in a specific heat. Actually, this nothing but the crossover from local moment regime to the classical spin nice regime, where the entropy is almost given by the isentropy. And okay, so then the evidence that this should be a crossover is actually already obtained here. Namely, we changed the system size from 6, L equal to 6 to 12. But actually, the curve doesn't change. Okay, so there is no dependence, almost no dependence of the specific key on L. It means that there should be no phase transition. Okay, so this already evidences that actually one crossover from which can be experimentally detected. And actually, most of the classical spin-ice material or dipole spin-ice material are looking at this. Okay. But more important thing happens on further cooling the system. And actually, specific heat drops dramatically to almost 0. And then we enter the plateau regime where the classical spin-ice picture applies. And in this regime, if we plot the charge susceptibility of the monopoles, which is given by this, actually already drops to 0, which means that complexity is 0, so there's no gapless charge excitations. So the charge degrees of freedom are completely frozen. Okay? But still, we observe a finite fluctuation of the local charge fluctuation of the monopoles or spin-ons, because n square, n is actually the Q, monopole charge, local monopole charge. So this guy stays constant. And actually, on further cooling, actually it slightly goes up, which may indicate that kinetic turn may give rise to some non-trivial behavior. Okay. But in this region, actually, there is another crossover where the entropy restarts decaying from the isentropy. And we cannot collect the reliable data even at an even lower temperature here. But I mean, it's already clear that it should go to 0 with some powers. And this is the plot of the specific heat in this region. Actually, this is quite low temperature, like 10 to the minus 3 here. And so around this temperature. So if we plot several data taken at the different system sizes, and then we can extrapolate these curves into the L infinity. So then we get some nice curve, like shown here in this solid line, gray solid line. And then we can also fit this curve. I mean, this is not really good fit, but we can fit total energy with some polynomials or the photon propagators, the contribution from the photon propagators, as we already talked about in the morning on the lattice. So then we can draw some curve for the contribution of photons to the total energy. So we can just try to optimize the velocity of the photons, light, as a kind of adjustable parameters, and then just try to fit this, for several points. I mean, the fitting is not very good, especially at the high temperature, because the photon, picture is only valid at the, in an exact sense, actually it valid at the ground state. And low temperature will be okay, but if you go up to a high temperature, like in a classical spin-ice regime, then it will break down. Actually, I will go back to that point when we talk about neutron scattering cross sections. Okay. In case we can try to fit with by allowing, by fixing the photon velocity, then we can get this kind of curve. And the specific heat behavior here is at least not inconsistent with that picture. Okay. So this is what we have for the second crossover. So I mentioned that this is a second crossover, and this is not phase transition. And here actually already plotted several curves, and they extrapolated all these data to L infinity. But here, these are the, here we plotted several curves taken at a different L. So it's already, converged to some continuous curve. So there should be no clear phase transitions. And at least there should be no first order phase transition. So this precludes the possibility that we have a first order phase transition from a confined phase to a deconfined phase, or classical spin-ice to the quantum spin-ice, or U1 spin liquid. Okay. So in that sense, U1 quantum spin liquid ground state or U1 spin liquid phase is stabilized only at the ground state. Okay. Yeah, this is suggested by this numerical data. I already mentioned that photons excitation may appear in a low temperature regime, so lowest temperature regime here. But this must be checked more seriously. And here we computed neutron scattering cross sections, which has already been given by the previous speaker. So then here is plots for spin flip channels for the polarized neutron spins, and this is a non-spin flip channel, and this is a total cross section. And we compare the results at different temperatures. Here is actually the high temperature, even above the Schottky peak in a specific heat. So there's almost no signature, except that there's a broad line like structure along the 111 direction. But on cooling, actually we see pinch point structure develops around each reciprocal Alice vectors except at the gamma point. So this is what we expect for the classical spin lines. So we already enter the classical spin lines regime in this temperature, actually here. And then we can further cool the system. So then we get the following. So this is one of magnitude smaller temperature here. So this is the temperature 0.01. It's pretty much low. And then we still see a pinch point-like feature, but actually we can see some possibly slight decay of the intensity around the reciprocal Alice vectors here, there. And we see some changes here, but it's not really, actually error, there's some error, so it's not really prominent feature. But further cooling the system to 10 to the minus 3, then now we clearly see a decay of the intensity around the gamma point or some other pinch points, remnant pinch points. So actually this has already been predicted to occur by non-compact gauge theory calculation by Owen, Benton, and which I already reviewed or in another way in the morning. And this should be exactly expected for the U1 quantum spin liquid state by photon propagators. Okay. And we also see changes for the non-spin flip channel. So I think it seems that it's quite easy by performing spin polarized neutron scattering experiments on, for instance, plasmodium or terbium particles, if the ground state may be U1 quantum spin liquid or not. Okay.
So in the quantum spinized space, do you also see a diffuse specifically?
Right. So this is our result. Well, so this is a specific kit, and this yellow curve is from the non-compact gauge theory calculations. So this strictly follow the T cube behavior at lowest temperature. And well, we cannot reach that temperature, that low temperature by numerics, but well, at least there's no inconsistency. That's what we can tell you.
So you mentioned something about n squared increasing at low temperatures.
I mean, this is a logarithmic scale, so it's not a big change, but actually stay constant and slightly increases by some factor.
Is it expected to increase?
Well, actually, this is close to phase transition to the Bose condensed phase. So clearly, the kinetic energy or the kinetic term in the Hamiltonian for the spin channel, spin-on channel should dominate, and that's why we can our spin-ons can go around like hexagons. So basically, even in the insulating materials, electrons have a kinetic energy, right? And that can be actually reflected in the S dot S, for instance. And when S dot S becomes prominent, and then electron can get kinetic energy. It's finite, but already capped, but still finite, and it can increase like this. So probably we are looking at some kind of similar features here. Okay. Okay, so let's skip this part because I'm trying to give a talk on this next week. So, so actually, we are going to show, next week I'm going to show the results of the magnetic field. But now let's focus on experiments.
And before that, can I ask a theoretical question?
Sure.
We also heard about these entanglement entropies previously.
Entanglement entropy.
Right. Possibly it is. No, I was just wondering whether it's known how the entanglement entropies go for these quantum spinning.
Okay. Yeah, that's a good question. Thank you for that question. Actually, they talk about when you talk about entanglement entropy, there are several cases. Clearly, there's a long-range entangled states or short-range entangled states. And except for 1D, which is actually trivial, all trivial, and all belong to the short-range entangled states. So non-trivial, topologically non-trivial states or deconfinement phase all belong to long-range entangled states. So the older spin liquids, non-trivial spin liquids, like except, okay, so it may depend on person to ask. You ask whether, some people, if there's no long-range magnetic order, then some people may favor terminology of the spin liquid, but I don't take that view. But if there is only a deconfined excitations, then we can say that it's a spin liquid. So then long-range entangled states, actually all the spin liquids, quantum spin liquids belong to the long-range entangled states. And this includes a valence bond solid state, for instance, and some other states. Actually, there are several states, actually 2 states, even for the long-range entangled states. One is the critical states. Okay. So then, length scale actually diverges, right? Or actually, it's not critical. It's just a stable phase. Or say gapped. And many spin liquid states belong to the gaps, have a gapped excitation, like in the case of the Z2 spin liquid, or some others, or Torricold model, and so on. But U1 quantum spin liquid have a gapless excitations. Okay, so that belong to this case. But nonetheless, it's not critical. Okay, it's just a stable phase. It's not critical, but some phase. So going back to the question, so if we compute long-range entanglement entropy, it should be extensive in this sense. And if you compute correlation length associated with this entanglement spectrum, so then it should diverge. And that calculation will be very, economic. It's not economic, and probably it's quite expensive. So that has never been done. But it's quite interesting. Will be an interesting observation numerically. Are there any more questions on the numerics? Okay. So then let's switch. Let me switch gear, and now you can be more relaxed. We are not talking anymore theoretical calculation, but just experiments. Just see what happens. Okay, let me start with the Placidinium particles. Okay, so this is our calculations at very high temperature. And this is inelastic scattering experiment, and taken at the particular energy of the 0.25 millielectron volt. So 0.25 millielectron volt is of the order of the 2 Kelvin. So it's low, but it's of the order of the exchange coupling. Okay, so then we see those features which is already seen in a numerical experiment. So it could be associated with the spinized physics. Okay, and if we look at the zero energy part, that's elastic scattering. But actually, this is not really true. When they analyze the data, okay, so you must be very careful. I mean, sometimes experimentalists may cheat. They need to analyze data so that they collect as many intensity from different points in a 3+1D space in energy and momentum. Okay, so then even though they are really interested in zero energy physics or static limit, they need to collect some data around the zero energy. So this has some energy resolution of the order of the point. I remember it's a 0.05 MeV or 0.1 MeV or so. So there is some region, finite region, where this data are treated. And then that means that this is energy resolution is of the order of the exchange coupling, right? So although it is actually focuses on omega equal to 0 MeV, there's a huge error bar. And actually this is almost energy integrated intensity. So that sometimes is missed in literature. And if we take this as energy integrated t equals 0, tau equal to 0, equal time scattering intensity, so then it can be compared with this or even at the lower temperature one. But experimentally, in the reciprocal Alice vector, here, there, and these spots, we already have a contribution, huge contribution from the nuclear peaks, okay, which is always there in a crystal. So it's quite hard to say that there's a decay in the intensity around here, but could be, okay. So in that sense, this is at least below the classical spinous regime, or maybe in a U1 quantum spin negative regime. Okay, so I already mentioned that in when we presented the numerics result. Pinch point intensity exactly at the pinch point will decay on cooling, and when enter the U1 spin liquid regime, then we see some decays. And actually, this is plotted here. I forgot to explain these graphs, but here actually I tried to show the comparison with non-compact gauge field theory calculation with new quantum numerical results. And here we see some decays at the reciprocal Alice vectors and in a U1 spin liquid regime. So that may have already occurred maybe here. There. But I mean, the resolution is not good enough, at least on the experimental side. So we need to wait for more experiments, or maybe a much higher resolution in the experiments.
So here, how does the temperature compare to the coupling strength?
I forgot to show the temperature. I think this should be 0.1 K. Yeah, here. This data is taken at 0.1 K, if I remember correctly. Yeah, it's a low enough temperature compared to the J. But, it's still higher than the crossover temperature we expected. And actually, recently, some more experiments from thermal conductivity appeared. Okay? Question? No? Okay. I mean, don't hesitate asking again, please. Okay. So then, actually, the thermal conductivity measurements have been performed, and then, thermal conductivity copper is actually scaled by C, specific heat times velocity times, this mean free path. Probably when it's divided by temperature or something. I think this is the correct relations. So actually, this is another way to prove the specific heat at low temperatures. But the problem occurs in the measurement of the thermal conductivity is that always the phonon dominates. And the people always say that the phonons will be gone at the low temperature, but who knows? So we cannot distinguish between the two. And well, and actually most of the cases, the phonon contribution dominates, as in this case, I mean plasmodium case. But the argument is that scattering time for the phonons is influenced by the magnetic scatterings. So then, if there's gapless excitation, then scattering will be more pronounced, and then it may be detected by this kind of measurement. But actually, analysis is not. I think it's still open. But in case they observe some increase at a very low temperature, which is comparable to our numerical experiment. Actually, this specific heat can be compared to thermal conductivity kappa directly, if you assume that the mean free path is almost constant. So then, actually, they already observed some upturn here. In addition to some feature at high temperature. So this could be, ascribed to the Newman spin-liquid physics, but I think it's clear that more experiments are required. And so in that sense, plasmodium zirconates, or maybe the stanates, or some other plasmodium particles could be a nice candidate to host the U1 spin-liquid ground state. And at least we can say so. And okay, so next thing is terbium titanium. So this is the material where I explained in the first talk yesterday that there's a lot of controversy on the experimental side, but in any case, there will be no long-range order at all. But actually, there is some sample dependence issue. And then one of my experimental collaborators took that problem seriously. Actually, they prepared a bunch of different crystals. Actually, this is not. Sometimes it's a powder, but this is actually, this could also be a phase diagram for the single crystals. And actually, they also compared the single crystal results and the powder results, and then it seemed that the consistency is really good between the two. And I think, actually, the idea is to intentionally introduce some, mixing of the terbium ions and the titanium ion, and change some concentration of stoichiometry concentration, and introduce X finite from 0.005 to minus 0.0125. It's less than 1%. It's that amazing. But in any case, this kind of small change actually makes the physics completely different. It's quite dangerous, right? And actually, this was not expected when they worked on classical spin-ice. And those classical spin-ice physics is very stable. It didn't change anything, although they changed some concentrations. That was also amazing part. But this is another amazing in the extreme limit. The other extreme limit, the results are so sensitive. So in this region, when X is nearly equal to 0 or slightly larger, then we see a sharp peak in the specific heat.
Just a quick question. I hope in the experiments they made sure that they were at equilibrium.
Right. yeah, we must also be careful. Yes, because mean free time or the relaxation time for the spinner's physics is quite long, particularly at low temperature. And that is true, especially when we work on classical spin-ice, because the gapless photon excitation is gone and just gives a flat, zero energy states, so which gives rise to extensive degeneracy. But when we include the quantum effects, now we have gapless excitations. So in that sense, it's a little bit easier to release entropy. Yeah, so I think this is, it's a kind of problem, satisfaction. But I think the situation is pretty much better than in classical spin-ice. Right? Okay.
How do we know the relaxation time? What's the
relaxation time? Ideally, we can wait for a long time. For instance, how the states decay or how the entropy is released. And if there's no more entropy released at that temperature, then okay, that should be possibly in the equilibrium. But it's also possible that it is trapped by a local minimum. Right?
But in experiments, you said so Monte Carlo, I can see this.
The same. And they need to wait. But unit, the unit for the time is also different, right? But that's a problem. But okay, so in any case, well, if there is a long-range order, it's much better, much easier. Right? But if you have a spin liquid or classical spin-ice, it's much harder. But in any case, we can compare the results taken at the different x. Okay? So then sometimes we see a sharp peaks in a specific heat, and sometimes not, just plot. And if they draw a phase diagram and plot the peak temperature for the specific heat, then these are those curve, this curve, and these points. So probably this would be a sign ascribed to the kind of phase transitions. Okay. And actually, those collaborators performed a lot of experiments, like susceptibility measurements or monetization measurements, and also inelastic neutron scattering. And then collecting all these experimental data, and then try to fit the data from the sometimes quantum Monte Carlo calculations, or sometimes classical Monte Carlo calculations, and so on. So then we end up with the choice of the parameter shown here. This is actually the kind of classical mean field results, which we published in the Arias paper, our Arias paper. And the result is that parameter for the J plus or Q term in null notation is much bigger than the U1 symmetric exchange term. And this term is comparable to the Ising exchange. Okay? So then we found that this level of the coupling constant, with this level of coupling constant, then we should have a ferroelectric quadrupole state. But that prediction has not been tested directly by experiments. So we need to wait for the polarized neutron scatterings. Yeah. So but
what does X do with this?
X.
So you're adding more logan instead of tagging.
Right. So they change slightly the concentration.
So is it like vacancies?
No, actually removes more titanium than for more terbium. So terbium ions, more are found in titanium side.
சரிங்க வந்தீங்க ஓகே நான் தெரிஞ்சுக்கிட்டேன்
Even x is 0, how perfect is the Python in that case?
Excuse me?
If x is equal to 0, so there is a perfect symmetric crystal. How perfect is the Python? I mean, how much is this?
I think it's not perfect crystal. Right? I think it's not possible to grow a perfect single crystal. There are always some substitutional effects. So actually, although and this is kind of information as an input when they grow a crystal. Right? They add several compounds, simpler compounds, and then mix, and they try to grow a single crystal by floating zone method. And they, I'm not expert. I'm not the right person to explain that. But in any case, they actually heat up the system at very high temperature and then mix. And just chemistry, right? Okay, so then X is controlled by the mixing ratio at the initial stage, but who knows at the end. So in that sense, the origin is not very clear. But at least, we can expect such a kind of change by quite tiny effect. Okay. And then, so since we are located in very close to the phase boundary, at least in the mean field level, so why not expect the phase transition to the spin-naked phase? Actually, this is SI means quantum spin-ice, and then that means the U1 quantum spin-naked. So it could be possible to cross this line. Okay. But this is not, not beyond imagination. But that could be possible. Okay. Okay. And last material is even more subtle material, yttrium titanate. Actually, all these particle series of materials have investigated by Ario in 60s. And then it was already known that this material shows a sharp fast order phase transition. And by any case, this is one of the audio results by Japanese group. They actually show inverse susceptibility here, which has almost behave like a ferromagnetic state, ferromagnetic behavior. And the Curie was temperature is ferromagnetic. And this is a magnetization curve. This is kind of soft magnet, so that the slope is finite, at least at 5K. But in any case, there is some features, show a feature, and this indicates some kind of small magnetic anisotropy okay, from these magnetization curves. But this is not really true. Magnetic anisotropy is quite large, as I have already explained when we introduced the model. But in any case, it's almost like it looks like soft and isotropic magnet. Okay. And then this is the neutron-scattering diffraction measurement. So diffraction means that diffraction means diffraction. So they are just looking at low energy part. Elastic scattering, and then they change the angle which control the Q vectors. Okay, on a single crystal. So then they observe a sharp increase on cooling the sample at around 0.2 or 0.2 Kelvin or 0.25 Kelvin. But actually, they need to wait for some time to see the change in intensity. And actually, this is the point at 111 point in the reciprocal series. So this is one of the reciprocal vector. So there is always nuclear contributions from the lattice. Okay, so most of the part actually it can be assigned to the lattice contribution or nuclear contribution, but see this change from almost 260 to 270. So this tiny change, like a 4%, it cannot be ignored actually. This is already enough for a spin 1/2 system like a one-Bohr magneton. And analysis of the neutron diffraction measurement already told us that there is a long-range ferromagnetic order with any spontaneous translational symmetry breaking. And the moment size is of the order of the 1 mu b. Okay. But at the same time, or since then, actually that material was also investigated a lot by European groups and Canadian groups, and many people worked on that material. And especially since there's some debate over the quantum spinized physics, and then there's a lot of experiments, more and more experiments. One of the experiments, or two experiments have been done for the inelastic neutron scattering at the high magnetic field. The reason why they focus on the high magnetic field is the following. At the zero magnetic field, it was found that sample dependency issue dominates. So if they measure, if they perform a measurement on a nice single crystal, it's possible to detect long-range order. But if that guy is not lucky enough, and then if they perform a measurement on very bad crystals, say, so then they don't see anything. So they just see broad features. So that's why people just want to focus on results at the high magnetic field. So then, if the magnetic field strength is much larger than any length scale, energy scale to solve the problem, so then there should be no such sample dependence issue. And another reason is that to extract the exchange parameters, it's better to go to some limit where a simple analysis may apply for comparison with the experiments. So at high field, where the spins are almost polarized and saturated, then it's possible to perform a linear spin wave approximation, and then directly compare to the measurements. So basically, these are the two different experimental data, which almost look the same, but actually the fitting are different. So
this, you say it's fully saturated. So this is fully saturated.
Close to, but not exactly.
So do you mean all spins are pointing along this, or just one fourth?
All the spins are nearly saturated along the field directions. Yeah, and actually they initially the Rosset performed the measurement under the 110 field, and Caldera et al. Oxford group performed measurements also at this same direction, and also I think it's also 111 if I remember correctly. And this already been appeared in the archive. And if they compare the results, experimental results are almost the same. But they made a different analysis. And if you look, and also signs are different. Signs are the same. Okay, sorry about that. Yeah, but this difference is quite a lot if we talk about the phase diagram. And although there's no gauge mean field calculations or any other analytical calculation which include all of the 4 exchange couplings, Sublime balance actually ignore this second come completely. And Sunbin Lee and myself and Lin Balance in the peer review paper, we dropped this last time. So we need to combine everything. But it seems that the Z plus minus term dominates. And what we expect from this result is that we should have a charge 1 Higgs ferromagnetic phase. Okay? And that is consistent with experiments which I will try to show right now. So this is our experimental results. Not from myself, but some of my experimental collaborators. And these are the this was published in 2012 at almost the same time. And we see we performed so polarized neutron scattering experiments at 0.3 Kelvin and at actually lower temperatures. And here we provide a comparison between the experiment and random phase approximation results. I didn't perform the gauge mean field calculation for this problem because it was provided by was being provided by the Ross et al. But if you look at this comparison, then it's already kind of satisfactory. And we see some evolution. We see some pinch point like anisotropic feature around the 111 point, and which you also see in numerics. And if you look at intensity around the 111 point, then it's also clear that it increases with on cooling. And this is another information from the spin polarized neutron scattering. That is what they call flipping ratio. So the neutron spins are now polarized at the incident source. But the neutron spin is when they come into the crystal, so then they are scattered. And some of them are spin flipped, or some of them spins will remain the same state. But if there is a large enough, big enough magnetic moment inside the crystal, and there are some domain structures, then they will be randomly scattered. So then they will lose the information of the initial spin state. And then we can take the ratio of the spin flipped and non-spin flipped intensity at some point. Then we can think about this ratio. And this is called the flipping ratio of neutron spins. And as I mentioned, when spins are fully polarized, it should be infinity. Okay? But when the spins are completely lose the initial information of the spin polarization, then it goes to 1. There's no distinction between the non-spin flip and spin flip channels. So usually this fact that the spin flip ratio decays to unity is kind of evidence, experimental evidence of having ferromagnetic domains. Okay? So we saw this. So it's kind of strong experimental proof that this is a ferromagnet. And actually we also see some hysteresis here. This is nothing but kind of observation of the first order phase transition. So we have a first order phase transition from a paramagnetic state, which could be in the Coulomb phase, in the sense that we see a pinch point like feature. But probably it's a classical Coulomb phase, but not the quantum. So then phase transition from that state to ferromagnetic state. Okay. And there is some figure here on the sample dependent issue, but it's quite complicated and some more recent results, so I will skip this. And there is another indication of another proof of the long range order in the crystal from the mirror cell experiment. Sorry, this is not the right one. Okay, next one. Here, actually, we plotted the normalized asymmetry of the signal from the mu itself. And usually, this signal should decay from 1 to a very small number. And when we have a perfect single crystal which completely orders ferromagnetically, then it should show us some sharp drop at the initial stage. This is okay, so real time. Sharp drop, we should see sharp drop, and then to 1/3, I guess, from 1 to 1/3, then decays gradually. And actually, ideally, we could see some wiggle associated with the muon spin rotations under the field. I mean, that's a precision. But it is not actually a necessary condition for the long-range order. And when muon is trapped at the side where the somehow moments cancel out each other, then we cannot see that. But in any case, this sudden drop in intensity, I mean asymmetry spectrum suggests that there is some big moment inside, at least locally. But actually, this sharp drop is not direct evidence of the long-range order, but just local moment. Okay, so there should be a local moment, both in a powder and also single crystal. So here we have already seen some drop here, but this drops much more quickly occurred than in a powder. Actually, here there should be the time scale resolution, which is limited by the instrumental resolution. And also if we plot the actually we can analyze these curves with some two exponential forms like this, and one expresses the fast decay here, and the other explains the slower decay. So the slower decaying component always matter when we talk about the low energy excitations. And then we can see some sudden drop in relaxation rate, or sometimes saturate or drops in the powder, and this is saturate in the single crystal. So it means that excitation becomes somehow frozen in the ordered phase. So it could be gapped. And the similar experiments were also performed at the magnetic field, under the magnetic field. So then we see a change of these curves under the magnetic field, and it goes up almost in parallel. And I'm not the expert of the mu cell, but this is called kind of the decoupling of muon spin under the field. And this is nothing but, they say that, muon people say that, take these results as evidence for the long-range order, but not just the local moment. Okay. This is yeah, oscillations sometimes seen and sometimes not seen. Actually, if we have a strong enough magnetic field, and then muons actually feel the field, then of course they precess, and then we see wiggle. But when muon is trapped in somehow remote site from the localized spins, and then it's hard. And
in a single crystal, we don't expect things like that. It should go through.
Go through what?
So maybe in a powder sample, perhaps can go to some region where it's canceling.
No, actually the muon can feel the small domains, right? So it's in the metallic system actually. Okay, maybe the other way around. Yeah, actually, but the length scale over which muon can feel the moment is actually it's finite. So, I mean, sometimes they can see, but sometimes not. Okay. And I can also time left. So 30 minutes or almost ending?
10 minutes.
10 minutes, okay. Then I can skip this, all this. Actually, we can develop a theory for that inside the Higgs phase by taking a unitary gauge, but not the Coulomb gauge. So unitary gauge is very convenient to describe the charge 1 Higgs phase. And actually, in the charge 1 Higgs phase, phase of the spin-ons, which becomes a Gaussian mode, but actually this is a ghost, and which is not real, and that mode is absorbed by gauge fields, and then it becomes, actually it provides a mass to the gauge particles, that is photons. Now photons are massive particle, spin 1 particle, and which has 3 degrees of freedom, but not 2. And then the remaining degrees of freedom are these massive gauge fields, excitations, and also the Higgs particle. So we should see at least 2 modes in the spectrum that I tried to mention. And these are some results taken at a high temperature, where the features almost are gapless. Okay, so I'm talking about the results at the ytterbium titanate. So this is an inelastic neutron scattering result experiment along some Q directions taken at 0.3 K above TC. And then we see gapless excitations, probably composed of a mixture of the gapless, almost gapless spin excitations and the gauge excitations. But below TC, we see a sharp mode at around 0.2 MeV, and which is not really dispositive. Probably this could be a Higgs mode. And we can, if we develop some more in a Higgs phase, then as I mentioned, we should see we can obtain actually the massive gauge excitations, which is described as a Broca fields. And then, actually below the Higgs bosons mode. And recently, amazing experiment has been done in JPOC in Japan. And actually they observed a low energy mode, which go to 0.04 or 0.05 MeV, even below the 0.2 MeV excitation for the Higgs mode. So, combining all these results, the ytterbium titanate, at least the sample, can be explained as from the viewpoint of the charge 1 Higgs ferromagnetic phase. Okay. So at least everything is consistent now. So now I should stop. The summary of these talks, the last third talk. So for ytterbium titanate, it seems that charge 1 Higgs ferromagnetic phase description looks working nicely for comparison with the experiment. And for the praseodymium materials, praseodymium and picros, this could be a nice candidate for hosting U1 quantum liquid ground state. But maybe better to improve the quality of the samples, because they say that mean free path for this sample is just 1 cubic unit cell. That is comparable to the 1 cubic unit cell. It's quite short, just a 10 angstrom or so. So it's clear that we need to improve the quality of the sample. I know myself, but I need to ask experimental colleagues. And also this is another candidate for the U1 spin liquid. That's a terbium titanate. Although the sample we worked on seems to be inside the ferroelectric coupled state, but possibly we can reach U1 quantum semi-negative state for this sample by tuning some stoichiometry, tuning the off-stoichiometry. Yeah. So those are the kind of recent, or I mean, yeah, now current advances in this field. Okay. Thank you for the nice your patience and also attention. Yeah. Thank you.
All right. Questions? The lifetime of muon is 2 microseconds, right?
Excuse me?
Lifetime of muon is 2 microseconds.
Lifetime?
Of a muon.
Oh, lifetime of muon?
And the why do you expect data up to 10 microseconds?
Okay, so
This one. The first one.
you're talking about which panel?
I'm saying the lifetime of a muon decays in 2 microseconds, right?
2 microseconds.
Yeah, the muon decays in 2 microseconds. And why do you expect data up to 10 microseconds?
Well, this is, they actually use a pulse muons. And I remember that they apply a pulse for the muons, and the duration is 50 nanoseconds or something. And then they observe the change in asymmetry. And the lifetime of muon, actually I'm not sure. Is that 2 microseconds? Yeah, could be, but I mean, I don't know. But usually the all the muon experiment actually show data up to some time scale like 10 or 5 or 10. Yeah. And actually the lowest time scale for this instrument, actually this is ISIS, taken out the ISIS, and probably the PSI provides a little bit better resolution for the time scale, but still it's not, I mean, if you can see the time scale, right? Smallest time scale, which is actually the this point. Okay, it's pretty much lower than it's kind of few nanoseconds. So at least we can, take this initial drop seriously. Okay? And this is nothing but evidence of the formation of local moment, and that is for sure. And for this part, I don't know. Okay. Maybe they took data, so they wanted to show it. Okay. Sorry, but I'm not the right person to ask that question.
In the CTQMC simulations for the spin systems, what is the sort of the largest system size that you can access?
We performed up to 12 by 12 by 12 times 4, almost 5,000 spins.
Is there a sharp signature for U1 spin?
Sharp.
Or when can we be confident that there is a U1 spin?
Well, actually, I already told you that U1 spin liquid is realized only at the ground state. So we haven't reached the ground state. It's not U1 spin liquid ground state. I mean, what we observe is not U1 spin ground state. But a crossover from a classical spin-at regime to a U1 spin liquid regime. But we haven't reached the ground state, unfortunately. But all the observation, like this photon dispersion, the photon contribution to the spin-spin correlation functions is completely consistent with non-compact gauge theory on the lattice, microlattice, and that is one of the evidence. And we are losing entropy like this, which looks at least consistent, well, not inconsistent with non-compact gauge field theory prediction. And our spin-ons are completely gapped, and combining everything, actually there's no, other candidates. Yeah.
Okay, so if there are no further questions, we should really thank Professor Onoda for his very nice and detailed lectures on orders tonight.
Thank you. Thank you.